Think of what you're saying. You can get it wrong and still you think that it's alright. Think of what I'm saying. We can work it out and get it straight. I'll say goodnight. We can work it out. We can work it out.
Okay, Volumes of Revolution. This is example number 3, the toughest of the 3 examples, and we can work it out. So you will be just fine. Hang on tight. It's not too terribly difficult, but I think the uncomfortable issue here is that we are going to be integrating with respect to y. We're going to be using limits of integration that are y limits, and our integrand is going to be in terms of y. So we've been through 3 examples so far. This is example 1, and we arrived at solution here. But what I want to emphasize, if you look at the picture, we talked about the bookshelving these circles from left to right. They start very, very small and increase in size. We're going to bookshelve them from 0 to 4. We added up that sum to get our final answer. The final answer there was 8 pi units cubed. Our second scenario, again, bookshelving these circles from left to right. In this case from -1 to 1, and we worked that integration problem and got 16/15 pi units cubed. So this last example is a little different. Number 3 in your packet, so no need to write this down, but here is the challenge that we can talk through for a moment. First curve is y equals x to the 2/3 power. The second curve is the vertical line, x equals 0. This line coincides with the y-axis. The third line is y equals 1, a horizontal line that travels through the y-axis at 1. Our direction and challenge is to rotate this enclosed region around the y-axis in order to find its volume. Let's look at the picture here. I've got a word of caution here. We're going around the y-axis. Everything that I stated earlier with regard to integral with a dy, integrand written in terms of y limits of integration, all those things are why you're seeing this caution exclamation point here. So here is the curve, x raised to the 2/3 power. The next curve is x equals 0. Again, it coincides with the y-axis. X equals 0. And the third curve, y equals 1. I kind of put that 1 up high so that we can see this region clearly. But if I graph that y equals 1, here is the straight line curve we're talking about. And hopefully clear to you now that we have surrounded or trapped or imprisoned a region, and this is the region I'm talking about. Remember, our directions are to rotate this flat region around the y-axis. So you have to see this in your mind's eye to picture what's going on. Rotate that around the y-axis, and in doing so, there's the y-axis. When I rotate that curve around the y-axis, I draw it just as a reflection over the y-axis, but I can really see this dotted region rotating around the y-axis, coming out toward me and then to the left, then away from me and then to the right, going and spinning faster and faster like a tornado. This thing kind of looks like a tornado in its finished product, but it goes slow at first and faster and faster, and you can see perhaps in your mind's eye this three-dimensional figure that appears, this three-dimensional figure that we are going to find the area of. Check it out. This time our circles are going from not left to right, but from bottom to top. Instead of bookshelving from left to right, I'm talking about stacking pancakes from low to high. So this is one such circle. Notice the thickness of this one such circle is a dy. And here's the radius. Easy to point the radius out in the picture. A little more difficult to find the radius when we get rolling here. But the sneak peek is, the last example we went top curve minus bottom curve to find that radius. In this instance, we're going to go right curve minus left curve in order to find that radius. Let's keep cruising. So now the challenge, I got to stack pancakes from 0 to 1. The lowest level of pancakes are 0 all the way up to the pancakes at 0 are super duper small. Then they begin getting larger and larger, and the stoppage point is when we get to that y value of 1. Okay, so again, I'm hoping that you are seeing this picture. We're going to stack pancakes from 0 to 1. Check it out. This time, same as always, we've got an area formula that we're going to utilize. Again, just an area of a circle. We're going to use pi r squared again. The difference in the integrand. Notice, we are writing this area formula in terms of y. And the integral is going to be tagged with that dy. That thickness of every pancake is an infinitesimally thin, very close to 0, approaching 0, dy, a small difference in y's. Alright, so again, the area formula for a circle is pi r squared dy. Our challenge is to find the area, the radius first that we can plug in for r. And we have to find it in terms of y. So I realize if you look back at your picture that we're going to go right curve minus left curve, but we can't be in terms of x's. We have to transform this equation so it's written in terms of y. The real challenge here is, what do you do algebraically to get x by itself? Well, if you take this and raise both sides to the 3/2 power, so raise the right hand side to the 3/2 power and raise the left hand side to the 3/2 power, you'll get exponents on the right that cancel top bottom relationships. 2's cancel top bottom, 3's cancel top bottom. You're left with just x to the first, or x. On the left hand side, you're going to be remaining with y raised to the 3/2 power. So now I've successfully written this equation in terms of y. X equals y to the 3/2 power. Such an important element of doing these problems successfully that a lot of calculus students miss the boat on. So this example 3, the toughest of the 3 for sure, and this is one of the reasons why. So I now realize when I go right curve minus left curve, I'm going y to the 3/2 minus 0. Our radius is y to the 3/2. Notice again the re-emphasis. We've got to write the radius in terms of y. So now we can plug this into our integral. Remember, the radius is y to the 3/2 power. That's something we still need to square. So here's the pi factored outside of the integral, and the radius is y to the 3/2 power. We're going stacking pancakes from lowest level 0, highest level 1. These are y limits of integration. Here's our radius, y to the 3/2 power. Don't forget, we've got to square that radius. You now all realize why that dy is necessary with the integral. Think about it. That integral symbol means summation. You're going to sum up all those little circles from very, very tiny to quite large, from 0 to 1, and we're going to add up all those areas. In fact, There's an infinite number of areas that we're going to add up, sum up. And when we do that and multiply it with our constant pi, we will have our volume answer for the three-dimensional figure that we create after taking these curves, rotating them around the y-axis. So this is just a simplistic rewrite here. I haven't integrated squat yet, still pi factored out, integrate between 0 and 1, and y to the 3/2 squared is just going to give me a y cubed. Again, I haven't integrated anything yet. We just went 3/2 squared here, and the 2's cancel, top, bottom, you're left with that y cubed. So now I've got to integrate. Add 1 to the exponent, divide by the new exponent. I have remaining a pi, and then add 1 to the exponent yields y to the 4th over 4, dividing by the new exponent. And then vertical line evaluation here. I'm going to evaluate that from 0 to 1. That ain't all bad. We can work this action. So we've got pi, and plug a 1 in. We're going FTC1, top limit goes in for y, minus, plug in the bottom limit for y. So we're going to get 1 to the 4th power, which is just 1. So we get 1/4 there, minus 0 to the 4th over 4, which is just 0. You can see plainly that our final answer here is going to be 1/4 pi units cubed. So some difficulties in the meat of the problem, but as you get closer to the end, things not terribly difficult. But you got to have the wherewithal in 3 locations. You got to have the wherewithal to know that your limits of integration are y's, your integrand's got to be written in terms of y, and this integral is not a dx scenario, it's a dy scenario. Alright, so there's 3 examples of the disk method. Should put you in good shape to complete your work for the disk method. And the method we have up and coming is a little different and a lot the same. But the washer method, we've gone disk method, the washer method is up next. This region's going to have a hole in it, much like a washer does. Stay tuned for that. Hope this is clear. Feel free to rewind if you need to see anything second time. And we'll look forward to visiting you further in the washer method, upcoming. Giddy up.